Welcome to this video lecture on the subject electronic circuit. So in this lecture we are going to discuss about voltage divider bias. So in the previous lecture we have discussed the fixed bias and collector to base bias circuit. So both the fixed bias and collector to base bias circuits are poor stable circuits. So fixed bias gives the collector current as unstable, and also collector to base bias is using the feedback path, it gives better stability. So compared to those circuits, voltage divider bias provides very stable bias circuit. So this is widely used in amplifier circuits. So here we have a circuit of voltage divider bias with common emitter amplifier circuit. In this, currents and voltages are nearly independent of any variations in beta. So consider the circuit here. The resistance R1, R2 provides the biasing to the transistor. It gives potential divider bias, and VCC is RC connected to the collector, and RE is grounded. So this is the common emitter amplifier circuit, and input signal is given to the base through coupling capacitor, and output is taken through C2 coupling capacitor from the collector. So C amplifier with voltage divider bias circuit is taken. And for analyzing the voltage divider bias, we take the capacitors as open circuited and consider only the biasing circuit. And also we are redraw the circuit for Thevenin's equivalent circuit. So consider here the VCC supply is drawn in series with R1 and parallel R2. So this forms the Thevenin's equivalent circuit. So we need to calculate the Thevenin resistance and Thevenin voltage for simplifying this voltage divider bias circuit. So first of all, we have taken the amplifier circuit and also voltage divider bias equivalent circuit. So from this, the RTH Thevenin resistance is calculated as R1 parallel with R2, and ETH is given by V voltage across R2. R2 into VCC divided by R1 plus R2. By applying the Kirchhoff's voltage law in clockwise direction in the Thevenin network, we get the equation as ETH minus IB into RTH minus VBE minus IE into RE equal to 0. So we get the base current as ETH minus VBE divided by RTH plus beta plus 1 into RE, and VCE equal to VCC minus IC into RC plus RE. So we have obtained the base current and collector voltages. And for approximate analysis, we consider Ri is greater than R2. So by applying this condition, we can derive the approximate analysis. So where IB is less than I1 and I1 is equal to nearly equal to I2. So by applying this condition, we get VB equal to R2 into VCC divided by R1 plus R2, where beta into RE is greater than 10R2. So from this we get the emitter current as VE divided by RE, and VE is equal to VB minus VBE. So from Kirchhoff's voltage law, we obtain VCE equal to VCC minus IC into RC minus IE into RE. So from this VCE is calculated as VCC minus IC into RC plus RE. And next we are going to calculate the load line analysis. For this we consider the transistor saturation level, where we get the maximum collector current, which is equal to VCC divided by RC plus RE. And for load line analysis we consider the cutoff values. So here collector current is taken as IC equal to 0 milliamps and VC equal to VCC. And for saturation, VC equal to 0 volt and IC equal to VCC divided by RC plus RE. So let's take the assessment. Draw the circuit of voltage divider bias. So voltage divider bias is drawn using the resistance R1, R2, which is given to the base of the transistor, and RC and RE. RE is connected to ground. So we have discussed the voltage divider bias circuit and the advantages of the voltage divider bias circuit. So compared to previous methods of fixed bias and collector to base bias, voltage divider bias is the widely used circuit in the amplifiers, because for the amplifier it acts to transistor have to act in an active region, so otherwise it cannot be act as a amplifier. So to amplify the weak signal, uh, so IC and VC values to be stabilized. So voltage divider bias have the low stability factor, which means it provides the better stability in the amplifier circuit. So thank you for listening.